Hi guys, good morning. We'll wait for 2 more minutes. Let everybody join. Then we'll start. Okay, then it's 7:05. I think we'll start. Right. Okay, so today we'll start with solid state people, right? Okay, right. So we already know certain things about solids, isn't it? From our lower classes, we have been studying about solids, isn't it? Say going for a flashback, right? So going back to your ninth class, uh, the chapter name was Matter in Our Surroundings. I don't know if you remember, right? So there, right, you defined matter, like, and you classified matter based on certain properties, right? So matter is anything which has mass and occupies space, right? Okay, and they say that this matter is made up of some kind of particles. Basically, these particles are going to be the building blocks of matter, right? We say that this particles which I'm talking about can be of two types, right? It can either be atoms or it can be molecules, right? We even saw in your previous things, right? When I said matter can be divided into two types, pure substances and mixtures, right? I said that in pure substances is made up of single entity. So that single entity, which what is I'm referring to as particles here, right? So the particle can either be atoms or molecules. I know if elements, the elementary particles are going to be atoms, And if it is compounds, the elementary particles are going to be molecules, right? Okay. And then there are going to be three main properties for these particles, right? So they say that between any two particle, right? Between any two particle, I'm going to have some kind of force of attraction, right? That's what keeps them together, right? Between two molecules of carbon dioxide, two molecules of H2O, there's going to be some kind of interaction, some kind of attractive force which exists between them, right? Which binds them together and which keeps them together, right? Okay, that is the first point. Between any two particles, I'm going to have some force of attraction, and that force is what is called as intermolecular or interparticle force of attraction, right? Okay, and second point being between any two particles, right? Between any two particles, I'm going to have some space in between them. Obviously, they will not be able to be like sticking together, right? Obviously, because I will have electrons in them, and both of them will have nucleus or nuclei to be very specific, and obviously they will undergo repulsion. So they will not be able to just stick together just like that. So there will always be some space between them, and that space is what is called as interparticle space or intermolecular space, right? And third point being all these particles will have kinetic energy. That means they will be randomly moving inside that particular matter, right? So based on these 3 points, right, I will be able to classify matter into three states of matter, right? One being solids, liquids, and gases, right? So now we know how these things are going to vary among solids, liquids, and gases, right? Say now for our interest, we have solids, right? So I know in solids they are going to be, say if I talk about interparticle force, right? So among all the three, solids will have the strongest forces of attraction, right? Between two particles, I am going to have the strongest forces of attraction, and obviously liquids will have intermediate, and gases will have the least force of attraction, right? And if you try to bring in an connection between your interparticle force and interparticle space, right? So obviously you can understand closer and closer the molecules are, or closer the particles are, the force of attraction is going to keep on increasing. It's going to be keeping on increasing, isn't it? Right? So obviously, for your solids, since your force is very high, that is understood. That makes us understand that the particle space, that is the interparticle space between the solids, are very small. They're very tightly packed, right? Okay, and then moving on to your kinetic energy, right? So it's all about how much restriction you're going to place for the particle for it to move. So obviously in solids, it's already they are very much tightly packed, right? So obviously they are very much restricted to move inside the particular solid, right? So if I compare the kinetic energies of solids, liquids, and gases, definitely solids will have minimum kinetic energy. Then your liquids and gases will have maximum kinetic energy, isn't it? And we can even speak in terms of entropy. Now we know so many concepts. Obviously, solids will have minimum entropy. And then your liquids will have little intermediate, and gases generally will have more entropy. Again, because of kinetic energy, right? Okay, so we already know this flashback of solids, liquids, and gases. We already know from our 9th or 10th class, right? So here we are going to see in depth, right? So we told that solids are going to have definite shape. I would say they're tightly packed, and most of the solids will have definite shape and all that, right? So we are interested in what will be this shape, right? What are the different types of shapes that solids can take, right? And we are going to see, like basically, we are going to make ourselves very small, and we are going to go inside the solid and see what exactly is happening, and that's what we are going to do in this chapter, right? So we are going to say there is this called as shortening ray machine. I don't know whether you watch cartoons, right? So there'll be a gun, and if you shoot them, that person will become very small. We even have examples, right? I don't know. You belong to this generation. I don't. Have you ever heard this movie of Little John in Tamil? Have you ever heard of this movie?
No, sir.
Okay. So that is the only movie in Tamil where a foreigner will act as a hero, right? So in that, it's not a great movie and all, but Jyotika will be the heroine, right? So that mean when I was small, It used to be a good movie, but I don't think you will, even YouTube, I think you will not be getting it. But anyway, so what happens there is something will happen and the guy will become so small, right? So anyways, that's what we are going to do here. We are going to make ourselves small, or at least imagine that we'll be so miniature in the miniature version of us, and we are going to go inside the solids, right, and see what exactly is there, right? Okay, but before moving on to all those, right, we have to understand what are the different types of solids we have, right? There are going to be two types of classification, right? So one, I would say, based on the chemical, like say the chemical properties in the sense, the what kind of bonds they have in between, say whether they have covalent bonds or whether they have ionic bonds or they have metallic bonds. So based on that, one classification is going to come, and the other classification is going to be based on whether they have a proper structure or not, right? So I know that solids generally have a proper shape, right? But there are solids, right? There are a good number of solids which doesn't have any proper shape, right? Okay, so moving on, right? So when I say solids, the first classification is going to be based on whether they have proper shape and proper arrangement and all that, right? So based on that, I will be able to classify them into two types. So one are what are called as your crystalline solids, and the next one is what is called as amorphous solids, right? Crystalline solids and amorphous solids, right? So I think from the name itself, you'll be able to understand. I know crystals generally will have a properly defined shapes, right? So if you take one crystal of say of sodium chloride, you take one crystal, right, and you view it under a microscope, right? So you will be able to see that there'll be proper arrangements. Like say, again, another example can be diamond. Like you know how diamond will have a network of covalent bonds, right? So all these things which have proper shape, like the proper patterns, if you have, those come under crystalline solids, right? And if I go to amorphous solids, obviously I am not going to have any proper arrangement, right? There is going to be random arrangement of particles, but still they are in solid phase. That's the point, right? And examples of amorphous solid can be your any type of powders, talcum powders, body powders, this powder, that powder, all types of powders generally comes under amorphous solids. And say other examples can be glass, right? Glass again is a super cooled liquid, we call it, isn't it? Glass, we call it a super cooled liquid. So again, glass and all comes under amorphous solids, right? So if I look at the differences between your what is that, crystalline solids and amorphous solids, I would say the first point of difference is this has a proper 3D arrangement, right? This has a proper 3D arrangement, right? So here it is going to be an irregular pattern. I don't have a proper arrangement. It is irregular pattern of arrangement. That's the first point of difference we need to understand between your uh, crystalline solids and amorphous solids, right? And what else, right? Now this is about the arrangement. Even if I talk about the shape, right? What shape they are going to be in, definitely amorphous solids are not going to have proper shape, right? So from the 3D arrangement, we'll be able to get proper shapes for your crystalline solids. Here, irregular shapes again, right? Okay. Now, next thing is there is going to be something called as an order, right? What do you mean by order? If I want to tell, right? If I go into my crystalline solid and see how is it, right? Say from one point, okay, let me put it like this. I'll not be able to show it to you. Okay, let me speak. Let me speak and make you understand, right? Say now I'm going to make myself small and go into the crystalline solid, right? Say now there are going to be say some n number of points where you can stand and observe what exactly is inside, right? Say you're going to the first, I'll take consider 2 3 points, right? There are 3 points, 3 points of observation. What do you mean by 3 points of observation? You're going to place yourself in these 3 points inside the crystalline solid and visualize how the structure looks everywhere, right? Okay. So from the first, okay, you stand on the first point and look at everything. For the second point, you look at everything. On the third point, you stand and look at everything. And what do you expect? Do you expect everything to be same? Everything to be same in the sense from the first, second, and third point, whatever you see, from whatever angle you see, are you going to see the same pattern everywhere? What do you expect?
Yes, sir. Yes, sir.
Hmm. So that's what we think, isn't it? Okay, fine. Now, let me give you a good analogy, right? So our houses are properly built, isn't it? They have proper arrangement. If I come this side 2 meters to the left, I have the kitchen. First I enter, I have a hall, and say next I have a bedroom, right? All these things are there, right? So now, if I stand in the hall and look at above, right, and if I stand inside the bedroom and look at above, will it be same? Obviously not,
No, sir.
isn't it? So that exactly is what is happening in your crystalline solids also. They have a proper arrangement, right? Say now at point one, you see you will see some kind of like see overall, yes, they have a proper arrangement, right? But we are going to look at ourselves. I mean, we're going to make ourselves small and look at it, go inside and see what is happening, right? So the very good analogy I gave you is the room, right? Or let me put it like this: you don't even have to take the entire house. Take your bedroom alone, right? You stand in one corner and look at the room, and you stand in the center of the room and look at your room. Definitely, you'll be seeing some differences, right? So that is what the analogy I can take here. So crystalline solids are not going to have long range order. What do you mean by long range order? Means like you do not have long range order. Means they have short range order, right? That means at different points from which if you visualize the crystalline solid, you will see different patterns. But overall, yes, they have a proper pattern, right? So how do I put it in words? Very simply, I can put that crystalline solids have short range order, right? Okay. Now, if I go to amorphous solids, randomly arranged, right? So the best example I can give you is, say you went for some trip, let's say near the sea, right? And you got lost, right, in a boat, right? Say where now sea is very vast, right? So in the middle of the sea, irrespective of whichever point you are going to be at, right, and you're going to observe the surrounding, you are going to see exactly same thing, right? You're going to see exactly the same thing, right? So obviously here I'm going to have a long range order from wherever you see, because it's randomly oriented. Everywhere it is randomly arranged, right? So obviously from whichever point you're going to visualize from inside the amorphous solid, you will almost find the same thing, right? So here they have long range order.
But sir, if we
Yes.
stand in the middle of the sea and see, then
Kanna, can you just
short.
increase your volume? I'm not able to listen.
Yes,
Okay.
sir. Am I audible
Ah,
now?
yes, yes, Kanna, tell
So,
me.
if we stand in the middle of the sea and see, everything is
Ah,
properly arranged, no, sir?
do you know that? I mean, everything is properly arranged. The thing is, everything is for you. It is properly arranged. But if you see, actually, some places I can have lesser depth. Some places I can have more depth. Sometimes some places I can have waves coming. So you see that everything is standing still, right? So you are observing it from the top layer. That's why you're seeing it like this. That's just an analogy. What I was trying to say. So the thing is, everything is randomly arranged. So wherever, irrespective of wherever you are, inside the amorphous solid, you will be eventually finding the same thing. That's what I'm trying to say. It is just an analogy. Obviously, yes, like correctly speaking, yes, they are properly arranged, but still, just to give you an example, right? There is obviously a difference between the house, like say a room in one corner and another corner, you see there'll be a difference, but there you will definitely not see a difference. So that analogy I wanted to bring in, like not an exact example. Okay, fine.
Okay, sir.
So yeah, that's the point. Second point, third point of difference: short range order and long range order. Right. Okay. Now next thing is I have a technical
Sir,
term. Yeah.
sir.
Tell me.
But in book I have seen that crystalline is a long range order and amorphous is short range order.
Mm, I don't think so. Short range order and long range order. Let me confirm it, Kana. This point I'll confirm. Let me also do my research and let come to you back. Okay, maybe next class.
Okay.
Okay, I'll look into it. Cool. So next is, so I'm going to give you a technical term. Right. So there is something called as, I would say, your crystalline solids are going to be anisotropic, or they will show anisotropy, and here they are going to show isotropy. Okay. Now again, what are these? Fine. So I have to rub these parts for me to understand, for me to explain. So explain you. Please take it down if you have it. Right. So here, what I'm going to do is I'm trying to measure a physical quantity. Say, it can be any physical quantity. It can be, say, refractive index, right? Or it can be any electrical property, resistance, anything, any physical quantity I am trying to measure, right? But so specifically, I am trying to measure that particular property in different directions of the solid, right? So if I look into an crystalline solid, right? So I know crystalline solids will have proper arrangement. Say, if I write it as proper arrangement, let me put it like this. Okay, they have proper arrangement, right? Okay, now we'll assume two directions, right? So the directions are, say, this is one direction. In this direction, I'm going to measure the physical quantity, say resistance, which I'm going to measure, right? Say another direction is this, assuming, right? Okay. So now what do you think? Will these, in these directions, the measured quantity, will it have the same value or different value?
Same, sir.
So right, okay, you're saying it's same, okay, but what you see is, or better way, right? So I have a very small torch, okay, I have a very small torch, okay. Now instead of assuming like we are measuring a physical quantity in this direction and this direction, let me put a torch and make the light rays go through this direction, and let me put a torch from down and make the light rays go in this direction, right? And you're going to observe from here. You are the observer here, and there is another observer here. Okay. Now tell me, will you observe the same amount of light or same intensity of light or whatever it is? Are you gonna observe same things coming out?
No, sir.
No,
No,
sir.
sir.
One is longer and one is shorter.
Diagonal is
That
short.
that is not the thing. Yeah, that is definitely a thing. So what I'm trying to tell you is that if I take the example of light rays, say in this case there is going to be more amount of interaction between the light rays and the particles inside, right? And in this direction there is not much of interactions, right? So definitely the rays which are coming out, right, are not going to be same. It can be in the form of length or intensity or wavelength or whatever the property of the light is, right? Definitely they're going to be different for these two, right? Same goes with your physical quantities also. If I measure resistance, if I measure some other refractive index or whatever the thing is, on different directions inside a crystalline solid, you are going to get different values, right? So, but sir, I have a proper value, right? I have a proper value for all the crystalline solids. These are all the average values what you have, which we use, right? But specifically speaking, at different directions inside a solid, since they have a proper arrangement, right? They're going to give me different values of that particular quantity measured if I'm going to measure it in different directions, right? And this property of the crystalline solid is what is called as your anisotropy, right? So how will I define anisotropy? It is the phenomenon where, right, a physical quantity measured at different directions yield different values. If you want a definition, I can give you. Please take it down. Anisotropy, right? Or in simple words, I would say that the physical quantities values will depend on which direction they are measured from, right? Anyways, so I'll give you. Anisotropy is the phenomenon where, right, anisotropy is a phenomenon where physical quantities measured along different directions. Physical quantities measured along different directions will yield different values. Will yield different values. Right? That's what is anisotropy. Right? And obviously you will be able to understand what isotropy is, right? Because it is like, how will I put it? It's randomly arranged your amorphous solid, right? So either you take this direction or this direction, right? So whatever the direction is, the physical quantity measured is going to have the same value, right? And that is my isotropy. So what is isotropy? When physical quantity is measured along different directions, yield the same value, right? So that phenomenon is what is called as isotropy, right? So your crystalline solids will show anisotropy, and your amorphous solids will show isotropy, right? So again, this is a very important point of difference between your crystalline. Yeah.
So they are randomly arranged, and how do you find that the physical properties to be same, sir? Like the measured physical properties?
I don't understand. Like if it's randomly arranged.
No, so they are randomly arranged, sir. So
Okay.
it can be like in one particular part, there can be no such particles present. Then when we find in one particular direction, then how will the measurement will be the same?
I understand what your concern is. So we are speaking about an ideal case, Kanna, right? So an ideal case, it is perfectly random, right? It is perfectly random. That means, how to put it? If you take a very small scale, like say 2 nanometers or 1 nanometer scale, you're going to take, right? And that 1 nanometer scale in one direction, another direction, 1 nanometer, definitely you'll find some difference, right? But if it is going to be ideally assumed that all the places I have equal number of particles and all the points in that particular space, I have equal, not equal arrangement, equal number of particles, right? So definitely overall, even though I'm going to have plus or minus, but still I'm not going to see this much of a difference here. That's what is important here. Definitely I will have some significant difference in the value when I'm going to measure it in different directions, right? But here, since it is randomly arranged, right, it is okay to assume for us, or it is okay for us to understand that at all the directions, since it's randomly arranged, right? So I'm going to have same value of the particular physical quantity. Right? That is how it is going to be, right? But yes, as you said, sometimes, or if ideally speaking, properly speaking, yes, there should be some difference in the value, but it is negligible, definitely. Okay.
Okay. Yes.
Right. Yeah. So that's about anisotropy and isotropy. Okay. Moving on to the next, the point of difference is, right. So next thing is about your boiling points and melting points, right? Your crystalline solids, this is about crystalline, this is about amorphous. So crystalline solids have sharp boiling points and melting points, right? That means, for example, if I have sodium chloride crystal, it will have an exact value. I don't know the exact value, I'm just telling you, say 200 degrees Celsius, right? That exact point, it will start melting, right? Okay. If I go to not isotropy, if I go to amorphous solids, right, they have a range of melting points and boiling points. Say, for example, if I take any powder, talcum powder or something, right, say I would say that the melting point is in the range of say 150 to 155 degrees Celsius. That means in this range they will melt, right? So here they have a sharp value of melting point or boiling. We cannot talk about boiling point. It's absurd because they are solids, right? So we can talk about only about melting points, right? Okay. So, but in case of your amorphous solids, they have a range of temperatures. So they have a range of melting points and melting point values, right? It is not a sharp value. Some range 150 to 155 or 155 to 160, something like that, right? So that's the next point of difference. Okay. And obviously, okay, yeah. So these are all the different points of differences between your crystalline solids and amorphous solids. And if you want examples, I can give you. say all metals, metallic solids, and say your even your polymers to some extent. Okay, I'll not call every polymer, especially polythene, right? All these things will have crystalline structure, and all salts, all the crystalline salts obviously will come into this MgCl2, NaCl, MgSO4. All these things will come under this, right? And here, if I go for your amorphous solids, say glass, rubber, all talcum powders, right? Say all these will come under your amorphous solids, right? So this is the first type of classification based on what kind of arrangement they have, whether they have a proper arrangement or whether they have a random arrangement, right? And a lot of times it has been asked difference between your crystalline and amorphous solids. A lot of times it has been asked in your board exams, right? Okay, we'll move on. We'll move on to the next classification. Right, so next classification, as I told you, is going to be based on, so we are going to see what kind of interparticle forces are existing between the solids, right? So if I look at what kind interparticle forces means, what kind of bonds I have between them, right? So based on that, I will be able to classify my solids into, right? So I have something called as covalent solids, right? So I have something called as covalent solids, and I have something called as metallic solids. I have something called as molecular solids, and lastly, I have something called as ionic solids, right? So these are the four broad classification. I think you will be able, from the name itself, you will be getting a fair idea of what I'm going to speak, right? So under covalent itself, I have three types. So I have polar, non-polar, and hydrogen bonded. Okay. So yeah, so this is the classification: covalent, metallic, molecular, ionic, and inside covalent I have polar, non-polar, and your hydrogen bonded solids. Okay, right. So we'll speak one by one. What are these? Right. Fine. So if I speak about covalent solids, right? So it is going to be a network of covalent bonds which binds the solid particles together, right? It is going to be a network of covalent bonds which binds the solids or the atoms together, right? And the best example I can give you for covalent solids is diamond, right? So I know how diamond looks between two carbon atoms, right? Or I know each carbon atom is tetrahedrally connected to four other carbon atoms, making a huge covalent network. And I know diamond is one of the hardest elements and all that, right? So diamond is a very good example for covalent solid. Okay. And what do you mean by polar, non-polar, and hydrogen bonded? I think you would have studied in your 11th class, right? So what do you mean by polar molecules? Or I think we even saw this polar or non-polar in your solutions, right? So I told you, like dissolves like. Polar solutes will dissolve only in polar solvents. Non-polar solutes will dissolve only in non-polar solvents. So what do you mean by polar? How will polarity arise in a bond?
Dipole.
Your volume kana.
Dipole.
Yeah, that is one of the answers you can give. So the examples of polar substances can be, say, HF or HCl or any other molecule which has a significant electronegativity difference between the bonding atoms, right? So obviously, you know, fluorine is going to be highly electronegative. Hydrogen is not electronegative. So I know what is going to happen. The electron cloud which is here, the two electrons which are shared here, it is not going to be at the center of these two nuclei. It is going to be more and more towards fluorine, right? So I know what I'm going to have. I'm going to have a partial negative charge on fluorine and partial positive charge on hydrogen, right? So these kind of molecules are what are called as polar molecules. So for For a molecule to be polar, the only requirement is that I need to have some electronegativity difference. It's not about highly electronegative. It's about high electronegativity difference between the bonding atoms, right? So if I have that, yes, they're going to be called as polar molecules. So examples of polar molecules, say HCl in solid state, like for polar molecules, SO2 in solid state, HCl in solid state. So I can understand there is definitely some electronegativity difference between the bonding atoms, between sulfur and oxygen, between hydrogen and chlorine, right? So all these comes under polar covalent solids, right? Okay. Now next, if I go for non-polar solids, right? So as the name again is exactly going to be the opposite of this. I should not have any electronegativity difference between the bonding atoms, right? So best example I can give you is iodine, which is in solid phase, right? Iodine in solid phase, right? Will be a very good example. Okay. And lastly, or even I can give the best example can be here. It can be this thing also. What is that? Your diamond also, because I know it's all carbon atoms there. Correct. It's all carbon atoms there. Okay. It's all carbon atoms there. So definitely there is no electronegativity difference. Comes under non-polar covalent solids. Right. Okay. And lastly, hydrogen bonded. Right. So we know what hydrogen bonding is, but fine. We'll keep it for some other day. I have so many questions which can be asked in hydrogen bonding regarding the concepts, but we'll keep it for some other day. Fine. So I know hydrogen bonded solids will have some amount of hydrogen bonding, right? Say the examples can be H2O, ice, basically, like not H2O in the sense, ice, solid phase. Even if I have ammonia, if you have it in solid phase, right? So again, all these comes under hydrogen bonded. What is that? Hydrogen bonded covalent solids. Okay. So that's about covalent solids, polar, non-polar, and hydrogen bonded, right? So we'll move on to metallic, right? So we know what metallic bond is, right? Between basically, metals. Say for example, if I take iron, right? See how strong it is, right? But it is just between two iron atoms, right? I have something called as an ionic bond, right? So how do I explain it? We'll see. How do I explain this metallic bonding? Now, if you have taken this down, I can rub this part. Right. Now, please understand that metals are highly electropositive in nature. That means what? They will be able to easily lose electrons. Right? Their electrons will be loosely bound to the nucleus, right? And they can be easily removed. Right? That's why we call them as electropositive in nature. Correct. Now, I'm going to have a structure like this for metallic solids, right? Say I'm going to have so many metal atoms like this. Okay, there are going to be so many layers, like this layer inside, on top of this, right? All places you are going to have metal atoms placed. Okay. Now, all these metal atoms are capable of giving electrons out. Correct, right? So what is going to happen is, I'm not going to call it as metal atoms. I will rather call them as metal kernels, because they are not exactly in atomic phase. Why? Because they have already lost electron. So what is going to happen is, in between two metal kernels, I'm going to have an electron. You can see, in between any two metal kernels, right? In between any two metal kernels, I'm going to have an electron placed, right? And obviously, this will be metals, since they have lost electrons, will be little positively charged, and electrons are there which are negatively charged. So I'm going to have a very strong arrangement of metal kernels and electrons like this, right? And that's why you see metals are generally very hard, right? So you can see that this particular electron is shared between these two, right? And obviously I can have one inside the plane and one on top of this plane, right? So one electron is basically shared by so many other metal kernels. And it is not like one metal kernel has only one electron to be shared. No, this metal kernel can have an interaction with this electron also, with this electron also, right? Obviously, you'll be able to understand what I'm trying to say, right? So I have metal kernels. In the metal kernels, I have a sea of electrons. Like the term we'll use is sea of electrons, right? So that is how I describe the structure of metals, metallic bonding, right? So obviously, I know all the metals, which aluminium, your zinc, your iron, right? All these things will come under metallic solids. Okay. Oh, I forgot certain things, people, right? So we have to talk. If I talk about the properties of covalent solids, I forgot about that, right? So covalent solids are generally bad conductors of electricity, right? They are generally, again, I can have some assumptions, right? Covalent solids are generally bad conductors of electricity and heat also, and not heat, but electricity for sure. That they are going to have what to say, less electrical conductivity. They are almost insulators, right? But if I go for your metallic solids, right? So metallic solids, since I have electrons which are free, right? They will be able to move inside the metal kernels, right? Thereby, they'll be able to conduct good amount of electricity, right? So metallic solids are good conductors of electricity. They are, I would say, they are better conductors of covalent solids for sure, right? So among covalent solids itself, I have polar, non-polar, and hydrogen bonded. Among these, polar will be little better conductors compared to your non-polar and hydrogen bonded. Okay, polar covalent solids will like little better than your non-polar and hydrogen bonded solids in conduction. Okay, and one more thing is, if I talk about the melting and boiling, okay, not boiling points, if we talk about the melting points, right? So since in covalent solids I have, okay, when I talk about the strength of the bonds here, that means between metallic bonds and the covalent bonds, I obviously know metallic bonds are stronger, right? Metallic bonds are stronger. So definitely when I compare the melting points of covalent solids and metallic solids, melting point of metallic solids will be little higher when compared to covalent solids. And again, if I go for the covalent solids for polar, non-polar, and hydrogen bonded, right? Generally, polar and hydrogen bonded, both of them, right? Polar and hydrogen bonded, both of them will have some good value of melting point compared to non-polar. Okay, so generally they will have less, but among these, polar and hydrogen bonded will have a little more melting point compared to non-polar. And compared to all the covalent solids, metallic solids will have more melting point. That is understood. Okay, fine. So that's about metallic solids. And your molecular solids, that is interesting, right? Ooh, actually, people, I did a very small mistake, right? The mistake is, whatever we discussed under your covalent solids are not covalent solids. These are molecular. I'm really sorry. Oh God. Right. Okay. So whatever we discussed here was molecular solids. I'm really sorry. Under molecular only, I have polar, non-polar, and hydrogen bonded. Please change it. Whatever the thing which you have written, if anything, please change it. Right. So the thing is, we are talking about we're talking about the type of interaction between two molecules or atoms, right? Between two molecules or atoms here, right? That means if I talk about H2 as a solid, right, I'm talking the force of attraction between two H2 molecules. Between two H2 molecules, you don't have a covalent bond. Between two hydrogen atoms, I have a covalent bond. Okay, so please don't make this mistake, whatever I did now, right? So on covalent solids, we'll see what exactly they are. And covalent solids, the best example is diamond. Yes, that is a very good example. But all the other examples we saw, H2O, I2 solid, and what else? HCl solid. All these are basically molecular solids, right? Why? Because you can understand between your HCl and HCl, between your HCl molecule and another HCl molecule, you do not have a covalent bond here. No, right? It is some other type of interaction. And obviously, I know what kind of interaction here. It is going to be dipole interactions. How is the dipole? Del plus, del minus, del plus, del minus. Now from this del minus to del plus, I can have a dipole interaction. So whenever I put a dotted line like this, right, it does not represent your covalent bond. It represents some other type of bond. It can be hydrogen bonding, or it can be a dipole interactions, right? So please change this. It is not covalent. It is molecular solids, because basically in molecular solids I have intermolecular forces which binds them, and intermolecular forces are not going to be covalent bonds or metallic bonds or ionic bonds. They are going to be, I would say, there are separate types of bonds in chemistry called as secondary bonds. Okay, so the entire bonds in chemistry can be of two types: primary, secondary. Under primary only you have your covalent bond, coordinate bond, ionic bond, metallic bond. All these things comes under primary types of bonds. And all the others, say hydrogen bonding, dipole interactions, van der Waals forces, right? Say all these things come under secondary types of bonds. So in polar molecular solids, you have only secondary bonds which binds the molecules or atoms together, right? So if at all going in specific, in your polar molecules, it is going to be mere dipole interactions like this, right? And in case of your non-polar, it is definitely going to be weakest, that is your van der Waals forces between two H2 molecule, between two Cl2, between two I2, right? So it is going to be pure van der Waals forces, and obviously in hydrogen bonded, it is going to be hydrogen bonded. Okay, that is the force which binds them together. Okay, fine. So we have made a mistake. We can't be this thing. So here it is going to be covalent. I'm sorry. Okay, yeah, fine. So under covalent, again, now between two atoms, between two particles, I'm going to have a proper covalent bond. I'm going to have a proper covalent bond, and the best example is diamond, because you see the particle which I'm talking about there is nothing but carbon atoms, right? So between two carbon atoms, what I have? A covalent bond, and that covalent entire network only makes up the solid, right? So here it is basically going to be covalent bond, and the best example I can give here is diamond or even graphite, right? So what happens there? Between two carbon atoms, I'm going to have a proper covalent bond there. Not like this. Okay, so that is about covalent bonds. And obviously, if I go to ionic bonds, it is going to be, sorry, ionic solids, it is going to be proper electrostatic force of attraction between the positive charge and the negative charge. Right? Between the positive and negative charge, I'm going to have a proper attractive force existing between them, and all the types of salt crystals, NaCl crystal, MgCl2 crystal, MgSO4 crystals, all these things will come under ionic solids. Okay, and again, speaking about your melting points or boiling, melting points, ionic solids will generally have the maximum melting point because they have the strongest of the forces, right? They have the highest melting point, right? And if I talk about conductivity, right? If I talk about conductors, generally metallic conductors and metallic solids and ionic solids are good conductors of electricity, and covalent solids and molecular solids are generally not so good conductors of electricity. But again, I can have some exceptions. I know graphite is a conductor, right? So that depends, but generally speaking, yes, molecular solids and covalent solids are not so good conductors of electricity, and your metallic and ionic, yes, they are good conductors of electricity. Okay, fine. So that is about the classification of solids, people. Right. So first starting with crystalline and amorphous, then you went on to see this molecular, metallic, covalent, and ionic. Right. So that is about the classification. Okay. Now in our syllabus, right? In our syllabus, we have only crystalline solids in our syllabus. We don't have amorphous solids. Right? We will not study about amorphous solids. We will be studying only about crystalline solids, right? And mostly we'll be studying only about ionic solids, mostly. But again, I can have certain places where you can have other types of solids coming also. But majority, right? Or we will not even speak about this. We don't have amorphous solid in our syllabus. We have only crystalline solids, right? So in crystalline solids, what I'm interested in is that I know they have proper arrangement and all those stuff. I am interested in what are all the possible arrangements, and if at all I have possible arrangements, which is a better structure or which will give it more rigid structure, right? All these things I'm going to investigate. Okay, so for that, for that we need to understand certain technical terms. Okay, so we'll go on about it. Okay, right. So what I'm going to do now is I am going to take a chunk of an crystalline solid, right? I'm going to make a chunk of a crystalline solid, okay? And what I'm going to do is that I am going to divide them into layers, right? Say this is the chunk, right? I took, right? This is the chunk I took for the crystalline solid, right? Now I'm going to divide them into layers, right? Divide them into layers means imaginary layers, right? Say now what I'm going to do is this is one line, second line, third line, fourth line. I can have n number of lines like this, vertical lines. This is one type of layers, right? And on top of this, I'm going to make horizontal lines also, right? I'm going to make the horizontal lines also, something like this. Okay, fine. Have you ever seen the movie? What is that movie called as Interstellar?
Sure.
Okay. So there will be a scene that he'll be caught inside that
Tesseract.
time space.
Tesseract.
Correct. He'll be inside the tesseract, right? He'll be able to see different timelines, right? So I don't know, like since you have seen the movie, maybe you'll be able to understand what I'm trying to say. But for others, right? It's better to watch that movie. It's actually a good movie. That's not only for this entirely. It's a very good movie. Anyways, so what will you see there is that the entire time lattice. Oh, I'm using some terms. Lattice. Okay. So the entire that structure, right? So there'll be these points where the horizontal lines and the vertical lines meet. Okay. So anyways, we'll not go into that. So please understand that. So this entire solid, this was the entire solid, right? So I just drew horizontal lines and vertical lines. Okay. And what you can see is some kind of arrangement here. What you can see is some kind of arrangement. So this entire arrangement of this solid is what is called as your space lattice, right? This entire arrangement or lattice generally speaks about the arrangement, the solid crystal arrangement of the solid, right? So this entire arrangement is what is called as your space lattice. Okay, fine. Now, inside this lattice, if I'm going to go inside this lattice, right? If I'm going to go inside the lattice, right? And I'm going to place myself somewhere, right? And all these, the meeting points which I have here, right? All these meeting points which I have here are what are called as lattice points. Right? All these meeting points which I have here are what are called as lattice points. Now, these lattice points cannot be chosen randomly, right? These lattice points cannot be chosen randomly, right? So how we have to choose them is like we have to place ourselves in different lattice points, right? Different points first, right? And from these points, what you observe, if your environment is exactly same, right? If your environment is exactly same, those points can be called as lattice points. In whichever points from you see, right? And like basically from all those points, if you see the same environment around me everywhere, right? And all those points can be called together as lattice points. Okay, right? Okay. So we understood what is space lattice. We understood what are lattice points. Okay. Now, what I'm going to do is I am going to search for something inside this. Right? I'm going to search for something inside this. What I'm going to search is that I am going to choose one smallest portion of this lattice. Right? I'm going to take one smallest possible portion of this lattice. Right? And how am I going to take? The condition is that if that particular smallest part, if it replicates itself in all the possible directions, I am going to get the space lattice, entire space lattice. Again, I repeat, right? from the space lattice, I am going to take a smallest possible portion, right? And how should be this portion? If this portion replicates itself in all the possible directions, right, I should be able to get the entire space lattice, right? Say for example, for just, it is not exactly correct what I'm doing here. Say I am going to take this portion out, this small portion which I have here. If I take it out, right, and obviously I understand that so many like the squares make up this big square, right? So this particular portion is what I want, right? And this particular portion, I'm going to give it a name. This particular portion is what is called as your unit cell, right? So how will I define a unit cell? Unit cell is the smallest portion of the space lattice, which when replicated in all the directions possible, will yield the space lattice, right? So unit cell, how do I define it? It is the smallest portion of the space lattice, which when replicated in all the possible directions, yield the entire space lattice. Understood? Right? So these three things, space lattice, lattice points, and unit cells, it need to be at your fingertips, because a lot of times we'll be using it. So many times in this chapter, we'll be using it, right? Okay, right. Right. So this is one thing which I have to say, right? So this entire space lattice which you are seeing, right? I have different types of space lattices, or this space lattices can also be called as crystal systems, right? This entire space lattice, how the arrangement and all these looks. I'll be, one second. Am I telling correctly? No, I am really sorry. It's not about the space lattice. It is about the unit cell, right? This unit cell can also be called a crystal system, but still, we'll not give it the name, right? So what I have to understand is this unit cell, right, can be of different shapes. One, what you see here is square, or like in 3D, if I speak, it is going to be a cube, right? Now I can have different shapes for this also. Say I can have something called as rhombohedron, and I have something called as orthorhombic. I have hexagonal. All these things are there, right? So all these things are there, giving it 7 different types of crystal systems are possible, right? 7 different types of crystal systems are possible, right? Now, how are we going to classify them? Is that I am going to take any crystal system, right? I am going to take any crystal system. Say if I take a cube, for example, bear with my diagram, please. Okay, so I have some cube with me, right? So I obviously have 6 parameters to look at, right? I have 6 if it's a cube, I know all the sides are same, all the angles are 90 degrees, I know. But if it is not a cube, some 3D shape, right? So this 3D shape can be studied if I study the 6 properties, 6 values. Okay. So what are the 6 values? There are going to be 3 lengths. That is the length, right? And you have 3 angles also. Okay. So what can be the 3 length? It does that. So if I can have some other color, so I can say that this can be 1 length, right? And this can be the 2nd length, and this can be the 3rd length. Okay. Basically, this I can call it as A, this I can call it as B, this I can call it as C, right? So these 3 are the length values. So depending on this, obviously for a cube, what will happen? A is equal to B is equal to C. That if that is the condition, it will become a cube, isn't it? Okay. Now I told you there are going to be 6 parameters. Only 3 of them we have, and obviously the other 3 are going to be angles. So I would say this is one angle, this is another angle, and this is another angle, right? So between AB, BC, and CA, what are the angles? And those will be called as alpha, beta, and gamma, right? A, B, C are the lengths, and alpha, beta, gamma are the angles. And obviously I know in a cube, alpha is equal to beta is equal to gamma is equal to 90 degrees. That will make it a cube, right? But I need not always have them equal. I need not always have them the angles to be 90 degrees. It can be so many combinations. There are going to be 7 combinations giving you 7 crystal systems, right? So that we'll see next class. Okay, what are all the different crystal systems? And for these crystal systems, again, I can have different types of unit cells. Okay, so we'll see what are these in depth next class, and we'll see for different unit cells, what are the other parameters, how many atoms can be there, what will be the efficiency of packing, right? And after all this, we'll be able to see what are the defects in solids anyways. So all these things we'll see next class. Okay, so I think it's time for you to go. So until then, I'll see you guys. Thank you so much. Bye bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yeah.
Thank